Welcome to the Ultimate Physics channel. In this video, I'm going to solve some problems on Einstein's postulates under special relativity. The first problem here is, during his youth, Einstein had this thought experiment in mind. What if he carried a mirror in his hand and traveled at the speed of light? What would he see in the mirror? That was his question. So one would probably expect a very interesting phenomenon to occur when one would be able to travel at that speed carrying a mirror, because one would expect to see strange things happening to the image on the mirror. So Einstein had something similar in his mind during his youth. So what is the answer to this question? See, in this case, according to Einstein's postulate, we know that if one would be able to travel at the speed of light, because we know that we cannot reach that speed, that is the speed of light in vacuum, which is the ultimate speed. So that is 3 into 10 power 8 meters per second, roughly, right? This is the speed of light. If one would be able to travel at that speed, it is possible to imagine strange things happening to our image on the mirror, if at all it is possible. So the question is that we're dealing with that aspect of our understanding of special relativity. See here, the thing that we have to remember is that since the observer, in this case Albert Einstein, let us say, he's carrying a mirror and he's able to see his image on the mirror, right? And right, his image is going to be on the mirror, right? So typically what would happen, since both observer here, which is Einstein, and the mirror are traveling at the speed of light, right, they are part of a single frame of reference, right? The entire thing is being an inertial frame of reference, because they're traveling at a constant velocity, so inertial frame of reference. So there wouldn't be any way for a person traveling, an observer traveling in an inertial frame of reference, to know that he is moving without comparison to another frame of reference, right? So if such a person is able to travel carrying a mirror at the speed of light, he wouldn't see anything abnormal. So nothing will happen. That is the answer to this question. Nothing abnormal would be observed. Just he would see his normal image on the mirror. Because people generally can imagine distortion in the image and all, but according to just the special relativity, a person traveling at constant velocity is in an inertial frame of reference. We are not considering any forces in this question, no acceleration, so nothing is there. So we don't get to see any distortion in the image on the mirror. So we would say that because it is an inertial frame of reference and it is traveling at a constant velocity, which is the speed of light, he wouldn't know without comparison to the outside world that he's traveling at that speed, and there would be therefore no changes, because if he is able to see some changes of his image, that would violate the principle of relativity, that would violate the postulate of relativity, that is he would be able to detect his motion without comparison to outside frame of reference. So that would violate the postulate. So we can clearly see that there would be any change because of such a motion. He would see his image as he would see when he is at rest. Right, let's move on to the next one. Prove that Einstein's second postulate about constancy of speed of light is inconsistent with the Galilean transformation. Okay, so this can be proved in different ways, but let us take an example here and try to prove this. Let us say we have a person, an observer, let us say, is traveling with a flashlight or a searchlight or whatever it is. And let's say is moving at a velocity u with respect to an earth-based observer. And he's flashing his searchlight, and light travels at velocity c, so we know that it is equal to c into 3 into 10 power 8. C is equal to 3 into 10 power 8 meters per second. That is the speed of light. Let us fix frames of reference to these two observers. Let us say that traveling observer is in a frame of reference S prime, and the earth-based observer, let us say, is in a frame of reference S. Now u is the relative velocity between S and S prime, and this observer is moving towards the earth-based observer. If that is the case, according to the Galilean transformation equations, the velocity of this light beam as measured by the earth-based observer has to be given by this expression Vx prime is equal to Vx minus u. This is the original expression for Galilean transformation equations. The inverse Galilean transformation equation is the velocity for the earth-based observer, that is equal to Vx is equal to Vx prime plus u. If I rearrange this equation, I'll get this right. Here, this is the velocity of the light beam as observed by the earth-based observer, and therefore Vx prime is c, the velocity of light, plus the relative velocity between the two frames is u. So Vx is equal to c plus u. So the velocity of light beam as observed by the earth-based observer is c plus u, which is greater than c, which is the speed of light, which is a constancy according to special relativity, which has a constancy. So constancy of speed of light, which is according to Einstein's postulate in special relativity, is violated. Right? So if you use Galilean transformation equations, which we have done here, constancy of speed of light for all observers is second postulate according to special theory of relativity is violated, and therefore we can conclude that Einstein's second postulate about constancy of speed of light is inconsistent with Galilean transformation equations. Right? So that solves the problem. Right. The third question is a flash bulb is located about 20 kilometers from an observer, right? And the bulb is fired. So the bulb is fired somewhere. An observer is standing here, let us say, and somewhere around at a distance of about 20 kilometers, the bulb is fired. It's a flash bulb, please remember that. So it is fired at that location at around 12 p.m. Right? Here it's given as 12 p.m. in the question. What is the actual time at which the bulb was fired? Because light takes a certain time to reach, right, the observer. So the idea that light takes a definite time to travel any distance because it has a constant speed is used here. It's a very simple problem. Therefore, the time at which the actual bulb was fired, let us say, is some del t, that is equal to the distance that it travels. Let us call that del s. Okay. Del s over the velocities, right? So that is the distance is 20 kilometers. So I write it as 20 into 10 power 3 meters over the speed of light. I know in units of meters per second. So I will write 3 into 10 power 8 meters per second. So I would get that as 20 over 3. That is, let us say 6.67 for the second decimal accuracy into 10 power minus 5 seconds, right? Or yeah, so I could write it as maybe 6.67 into 10 power minus 2 millisecond, right? So the bulb would have been fired 6.67 into 10 power minus 2 milliseconds before 12 p.m. so that the flash can be observed at 12 p.m. right? So that is the answer to that question. Okay, so let's move to the next one. Yeah. Paul Ehrenfest suggested a thought experiment because those days, special relativity, several people proposed a lot different thought experiments to understand the ideas of special relativity. So Paul Ehrenfest suggested a thought experiment to illustrate the dramatically different observations that might be expected dependent on whether light moved relative to a stationary ether or according to Einstein's second postulate. Those were the days when people were trying to realize the fact that the existence of ether couldn't be proved. So several such thought experiments were proposed. One such experiment was proposed by Paul Ehrenfest, where he says that suppose that you are seated at the center of a huge dark sphere with a radius of 3 to 10 power 8 meters and with its inner surface highly reflective. So you have a large sphere whose inner surface is reflective and the radius of the sphere is equal to the distance that light would travel in 1 second. That is light second. That is the radius of the sphere and its inner surface is highly reflective. A source at the center emits a very brief flash which moves outward through the darkness with uniform intensity as an expanding spherical wave. What would you see during the first 3 seconds after the emission of the flash if first condition is the sphere moved through the ether at a constant 30 kilometers per second and second condition is if Einstein's second postulate is correct? Such a thought experiment would be able to tell us which one of the two is true or what would happen to such a light sphere, expanding light sphere. So we can imagine that this is a large dark sphere whose radius is equal to 1 light second, which is 3 into 10 power 8 meters. Okay. Let us say a source of light is being flashed at the center of the sphere, and let us say an observer is sitting on top of it, and the flash starts traveling as a spherical wave outward from the source like this, right? Uniformly expanding spherical wave of light. So what would happen in the first 3 seconds? That is the question here. First 3 seconds, what could one expect after the emission of the flash? If the whole sphere, the dark sphere, is moving at a constant 30 kilometers. The significance of this number, 30 kilometers per second, is actually the speed of Earth through space. So if ether is present, then one would be able to detect the speed with respect to ether. So that those were the days when still the idea of ether was plaguing the scientists. So here that speed has been considered, because if first case is true, then ether's presence could be understood. If that is not true, then second case, that is Einstein's postulate, must be correct. So that was the experiment that Paul Ehrenfest thought experiment that Paul Ehrenfest came up with. Einstein, remember, regarded Paul Ehrenfest as one of the greatest teachers, right? So one could imagine how serious, this thought experiment was, right? So the first part, one would say that if this is the case, the light would travel, the spherical wave from the source would travel to the wall, a reflective wall of the inner wall of the sphere. It would take 1 second, and then any reflection from that wall, again for it to reach the center, that is where the observer is present, would take another 1 second. So clearly 2 seconds of the given 3 seconds in the problem would be spent for observation of the light flash. But for the first case, one would see that, let me write down here. We would see a large plane of light reflected back, which is perpendicular to the direction of travel. Because if the direction of travel is, let us say, in this particular arbitrary direction that I am marking here for the direction of V, then in a perpendicular plane, the light flash would return faster than in any other direction on the sphere. Okay, so that understanding we should have. Why? Because we have already derived this thing in even our problems on Michelson-Morley experiment. I suggest that that video should be checked by the viewers, where I have discussed as to why we cross a river, for example. There is a problem where two boatsmen travel in directions upstream, downstream, and perpendicular to this current, river current, in a direction perpendicular to the river current. If river is flowing in this way with the velocity v, and if the boatsmen are able to travel with the speed c, the boatsman, let us say A, travels perpendicular because his velocity is v like this, and the boatsman, let us say B, travels parallel upstream and downstream. Now in that problem, we had discussed a solution where we found out that the guy, that is boatsman A, who travels perpendicular to the current, takes a shorter time compared to the boatsman B to reach the destination and complete the race. So who is the winner here? Boat A. Direction is perpendicular to the river current. Similarly here, the ether current is flowing, and the sphere, dark sphere, is traveling in ether, and the direction perpendicular to that is this direction. So you have a plane here, therefore, because it is in 3-dimensional sphere, and there is a plane that is perpendicular to that direction. So the perpendicular direction is here a large circular plane. Okay, so in that direction, light would travel faster than in any other arbitrary direction, and therefore any reflection from that greater plane or larger plane would reach the observer at the center first, and therefore you would see a large circle of light flashing reflected from the great circle on the sphere. That is after 2 seconds. Then after that it would die out, that we don't need now. Basically he would see in 2 seconds a circle of light. Now if this is for the first case, that is if this thing is moving at a speed of v, through ether. What about the second case where in Einstein's postulate we know is true? In that case, light would travel uniformly in all directions and expand as a large sphere, and therefore the entire dark sphere will be illuminated after 2 seconds for a moment, and then again the sphere would become dark again. So the two cases are therefore different. In the first case, a large circle of light would be observed by the observer at the center, whereas in the second case, he would see the entire dark sphere getting illuminated for once briefly after 2 seconds, flashing, and then again the entire sphere would go dark again. So that is the conclusion we can give for this problem. Okay, let's move on to the next one. Here, a train is 1 kilometer long and moving at 150 kilometers per hour speed with respect to the stationary platform. Two flashes of lightning strike the front and the back end of the train at points A prime and B prime respectively. The points A prime and B prime on the train, as well as the corresponding points A and B on the platform as well, are scorched in the process. An observer standing on the platform at point C, midway between the points A and B, measures the flashes to be simultaneous, whereas an observer traveling in the train located at C prime, which is the midway between A prime and B prime, does not think so. How much does the traveling observer measure between the two flashes? How much time it is actually, right? So how much time does the traveling observer measure between the two flashes? This is the question here. Okay. So how do we approach this problem? Let us say we have a train coach here. Let's try to imagine it. And C prime means the midpoint between A prime here and B prime here. And then we can imagine the platform observer is on the platform. B, A are the points. C is the midpoint for him. And we see that two flashes of lightning scorch the points simultaneously. That is the points B, B prime, and A prime, A. Right? So, under this condition, the observer here at C, that is the observer on the platform, measures these two events, event 1 and event 2, that is scorching of A prime A, scorching of B prime B by the lightning flash, to be simultaneous. But the train is traveling at a speed V is equal to 150 kilometers per hour. So any observer sitting here at C prime would find that these two events 1 and 2 are not simultaneous. So for this observer, the two lightning flashes do not strike at the same time, because ground observer has already observed that it is at the same time. So according to the idea of simultaneity in special theory of relativity, this is not possible for the observer on the train. Right? So we can use directly expressions of simultaneity to prove this, to find out the time difference, but we should not do that in this case, because we are trying to solve the problems only using just idea of Einstein's postulate. So we should be doing it in another way, right? How can we solve that? It's very simple. In this case, we can see that according to the ground observer, from the center, the flashes C, let us say prime, The flashes from the light waves from the flash travel like this towards the center of the train or the coach, like this. And these two wavefronts do not arrive at the same time, because for the observer at C prime they are not simultaneous, right? So there is a time difference, and that time difference is what is asked in the question. Let us call the time difference as del t, which is time at which the flash strikes the rear TR minus the time at which it strikes the front TF, or the time at which the light wave from the rear, because if the train is traveling like this is the rear portion and this is the front, and it is traveling at 150 km per hour. So that is TR minus TF, let us say. And the distance, the length of the train is given here as 1 kilometers, right? So the whole length is 1 kilometers. So from center to this point it is 500 meters. And therefore, if light wave travels this way towards the left from the front, then we can say that for TR we have to write the time as distance 500 meters over C minus V. In our original equations we have done it for even the fourth problem. In that way we can do it here in the previous video. So you can see that it is C minus V, that is 3 into 10 power 8, which is velocity of light, and that is affected by this motion 150 kilometers per hour, that can be converted to 150 over 3600. This is kilometers, so it is 150 into 10 power 3. So this would basically mean is 150 by 3.6. So 150 over 3.6. That is meters per second conversion for the kilometer per hour units of the speed of the train. So I say it is 150 over 3.6 minus, again this distance also is 500 over 3 into 10 power 8 plus 150 over 3.6. So this is obtained from this, the time is here equal to some distance L, let us say, by C minus V minus L over C plus V. This is the formula we have used here to calculate the time difference. And because the train is traveling towards the right, TR is greater than TF, so that's what we are doing here. TR minus TF, that is time for the wave front to travel from the rear of the train, which is TR, is greater than time for the waves to travel from the front, because these waves are going to take some more time to travel to the center compared to these waves. And therefore this is the difference, and if this can be worked out, the answer to this problem is going to be 4.63 into 10 power minus 13 seconds. This is the time difference between the two events, the waves being counted here at the center by C prime for arrival of the wavefronts from the rear and the front. That is the time difference, and that is what is asked in the question. So that is the conclusion we can arrive at. Okay. Let's move to the next problem. 3 points A prime, B prime, and C prime are at rest in frame S prime, which moves with respect to frame S at a speed v in the plus x direction. The point C prime is located exactly midway between points A and B, At time t prime, a light flash occurs at c prime and expands outward as a spherical wave. So there are two parts here. According to an observer in S prime, do the wavefronts arrive at A prime and B prime simultaneously? According to the observer in S, do the wavefronts arrive at A prime and B prime simultaneously? If the answer to either A or B above is no, what is the difference in their arrival times? At which point the wavefronts arrive first? Which of the 2 points the wavefronts arrive first? So it is somewhat similar to the previous problem, but here they have not mentioned a train. So we have to assume that there are two different frames of reference here. Okay. Let us call the first frame of reference S prime, and C prime is the midpoint between two other points A prime and B prime, and a source of light is at the center here, and therefore waves are traveling outward in this particular case towards the 2 points A prime and B prime according to the question. And the whole S prime is traveling with the velocity v with respect to another frame of reference S, which is at rest. Right? So here the question is, at time t prime, the light flash occurs at c prime and expands outward as a spherical wave, which we have depicted here. First question is, according to an observer here at S prime, do the wavefronts arrive at A prime and B prime simultaneously? So the first part of the question, A is answer is yes. So for an observer in S prime, the two wavefronts going right towards the right and towards the left, they are going to travel equal distances because C prime is midpoint between A prime and B prime. Equal distances light wave is going to travel, so it is true. Two waves travel at the same time, so waves arrive simultaneously. At A prime and B prime. Okay. Now what about the part B part? B part. What about the observer? According to observer S, right? That is the second part here. So S is stationary with respect to S prime. So obviously the two events should not occur simultaneously. Therefore, for the observer in the frame of reference, the answer is no. The waves arriving right at A and B points do not arrive. The waves arriving at A and B do not arrive simultaneously. So simultaneity is affected here for one observer, right? That is the observer in this particular frame of reference here. If a person is standing here, you would find that A waves arriving at A prime and B prime do not arrive simultaneously. Okay, so it's A prime and B prime, right? Waves arrive at A prime and B prime. For him, it is therefore not simultaneous. Now, there is another part of the question, right? If the answer to either A or B above is no, what is the difference in their arrival times? At which point the waves front arrive first? So here the answer to the second part is no, so we have to deal with the third part now. Let us take the difference here to be some del t, because the answer here we have given as no. Let us calculate the difference, that is del t. Now in this particular case, since the traveling is outward, the waves are traveling outward and towards A prime and B prime, we can clearly see that because of the motion in this particular direction with the velocity v, the waves arriving at B prime is going to be first compared to waves reaching A prime, because the motion is to the advantage in the right side. Waves are also traveling in the same direction, therefore to that direction waves have to go first. So we can clearly see that the waves are arriving at B prime first. And why we have to find out, right? Further we have to calculate this del t. So again, like the river problem here, you have upstream, downstream, right? So when we do the velocity here, we will do c plus v and c minus v. Obviously the larger velocity in this case is c plus v, so it is to the right, right? Right, now we can calculate this the same way, therefore, for the distance. Let us say that is L prime is the distance for the traveling observer from C prime to B prime. It is L prime, let us say. We say that it is C minus V minus another L prime to the left, that is C plus V. Therefore, if we can calculate by taking an LCM here in this case as well, we say L prime C plus V minus L prime C minus V, and therefore we will solve it to be equal to 2L prime V over C square plus V square. This is the expression for the time difference between the arrival of the waves at A prime and B prime according to the observer at S. So because this observer here would measure them to be 0, del t prime for him would be 0, but for this observer del t would be not equal to 0, and that would be equal to 2L prime V over C squared minus V squared. So we can clearly therefore see that in this case the two waves do not arrive at the same time for the observer who is in relative motion with respect to the S prime observer. Right, let's move on to the next one. If the speed of light c is less than what it is, would the relativistic phenomena be more or less conspicuous? That is the question here. Very simple question here. C is now 3 into 10 power 8 meters per second, as we know it. If C is less than this value, whether the relativistic phenomena that we observe, any of the relativistic phenomena that we observe, whether they would be more or less prominent or conspicuous. That is the question here. The answer would be straight away more conspicuous, definitely. How? That is the question, right? Though C is less, all our comparisons we can do as a ratio of the velocity attainable by us in any phenomenon. In any phenomenon, the velocity that we observe to the velocity of light. This is how comparisons are done, because in relativity also we know all the expressions have a parameter called beta, which is V over C. And the Lorentz factor gamma is equal to 1 over square root of 1 minus V squared over C squared, which is of course 1 over square root of 1 minus beta squared. Therefore, we can clearly see that if suppose C is less than what it is now, according to this expression, beta would be more. That is, the ratio between V over C would be more for any given velocity if C is less. Right? That is the first condition. If that is the case, what about gamma? If beta is more, 1 over this will be more as well, because it is in the denominator, and beta is more. That means the square root of this is less. If this is less, the numerator is 1. So the gamma factor would be, the Lorentz factor would be greater. If the Lorentz factor is greater, obviously relativistic phenomena would be more conspicuous. Why? Because we know that, for example, in length contraction, let us take, there is one relativistic phenomena that we can straight away understand. It is L naught 1 minus beta square, like this, right? So if this factor beta is more, that means the contraction of the original length L naught is going to be much more, so more contraction. So So that is more conspicuous. Similarly, for time dilation, let us say take t is equal to, we know that it is t naught over this factor, right? T naught over 1 minus. Here also, if beta is more, then more dilation. That would result in more dilation. So these are examples of two relativistic phenomena that become more pronounced because of a variation in C. Because if C is less, beta becomes more. Therefore, this is a conclusion we can give. Therefore, the answer to this question is more conspicuous. Right? So that concludes some of the problems that we wanted to discuss on this topic. That is Einstein's postulates on special relativity.